Good evening, everyone. My name is Yan Yan. I'm from Department of Physics and Astronomy. Today, I will be talking with you about my research on on blackouts in the power grids. When I was a kid, I had to experience at least one blackout each summer. To me, blackout meant no light, no air conditioner, no TV, and it was really annoying. But a real blackout could be much, much worse than that. It is a catastrophe. On Thursday, August 14, 2003, there was a widespread large blackout over the northeastern parts and midwestern parts of the United States and the province of Ontario in Canada. At that time, some areas lost water pressure. Cellular communication were interrupted. All trains coming into and out of New York City were shut down, and thousands of flights were canceled, and passengers were stuck in the airport. An estimate of over 55 million people has been affected by this event. Before we dig up the reason of this blackout, let's first have a look on how the power grid works. Electrical power are not easily to be stored over an extended period of time. It is usually consumed within seconds after being produced. That means that how much energy we used from the power grid must be matched with how much supply to the power grid, and must also match the transmission ability of our power grid. The supply to the power grid is provided by various generators like wind power, the solar power, the nuclear power. These generators work in a coherent way. When the load is not equal to the supply power, some of the generators will work faster and faster. Some others will work very slow, and it loses synchrony. To prevent irrecoverable damage, the system will automatically cut off some of the generators, and then we lost power. Let's go back to 2003 to see what happens. The blackout started with 3 initial transmission line failures in Ohio, just because the contacts with tree in summer, and it caused power transfer. However, because of the misoperation of engineers in Ohio, the amount of transferred power exceeded the transmission ability of the transmission lines, so it caused new failure. 40 minutes later, the eastward flow was stuck, and there was a huge power deficiency in New York. And it was a cascade because more generators were offline, and more transmission lines failed again. Within 10 seconds, Ontario was separated. After 2 minutes, New Jersey was separated. We lost 255 generators in total, and most of them happened within the last 2 minutes. A lot of research effort has been put into the study of the reason of cascade blackout and how to prevent it in the future, and it is a real challenge. It is not only because everything happened in a very short time scale, but also because our power grid is such a human precisely controlled system that human involvement adds additional uncertainty to this problem. Here comes to my research as a physicist. As a physicist, our working style is we abstract data from real phenomena, we build a theoretical model, and then we want to explain what happens and why it happens. And then we predict what will happen in the future. This is the cascade blackout in physicists' eyes. Everything starts from a very initial small failure, and for some reason, it amplified itself to cause more failures, and finally, it led to the great separated and large blackout. From the real cascade data, we are able to build a simplified model. This model has the exactly same statistical properties as a real one, which means that what is observed in this simplified model could predict what will happen in the future, or it's just a cascade event happened in the past. And this simplified model we are able to do very fast simulation on every possible cascade events in the United States power grid. And we can change the initial condition of this model to mimic different times of a day and different seasons of a year. This model is used to explain how the cascade behavior amplified itself and how can we say about the anticipated blackout size in the future. This is one of our findings. Among all the transmission lines in the power grid, there are only a small fraction of them could have a chance to fail in all possible cascades. That means when there is a cascade failure, we can save our energy and save our time by only paying attention to these susceptible transmission lines. And we can even do better. We find among these susceptible lines, there's even smaller group, which means transmission lines within the same group would be more likely to happen together. But it is less possible that two transmission lines from different groups will fail together. But these very small probabilities between groups are responsible for the amplification of cascade. How can we stop the cascade blackouts from this? One way is we eliminate the size of these small groups. The other way is that we cut off the probability connection between the groups. So the cascade loses ability to amplify itself. Our power grid are experiencing an update to accommodate the increasing need of power trading. More and more interconnections across the states are being built. However, although we can benefit from these interconnections because we can get cheaper power and we can get diverse power resources, we are paying a price that this interconnection actually will enhance the probability connection between groups, and that means there might be an even larger blackout in the future. So when you enjoy the benefit from the update of power grid, please be aware that one day we might face an even larger blackout than ever before. I'm Yan Yan. I'm a physicist working on eliminating every possibility of both large blackouts and small blackouts. And thank you.